Hello, everybody. Welcome to the second half of this special session on the centenary of general relativity. Our next speaker is Professor Edward Witten from the Institute for Advanced Study in Princeton. Professor Witten is a major figure in the development of string theory. He's also found unexpected connections with mathematics and is the only physicist to ever win the Fields Medal in mathematics. He's going to talk to us today about what every physicist should know about string theory.
Thank you so much. So for those of you from other areas of physics, and also for students who aren't yet string theorists, I'll be telling you what you might want to know about string theory if you're not working in that field. Of course, if you do want to work in string theory, there are lots of more specialized things you'd want to learn. For those who are string theorists, I won't be saying anything that's remotely new, as will become clear. Juan Maldacena's talk after mine will perhaps be a little more contemporary, but possibly I'll help remind us to appreciate some of the wonderful things that we sometimes come to take for granted. So, as I said, I'll be trying to explain today the minimum that any physicist might want to know about string theory. I'll try to give answers to a couple of basic questions. How does string theory generalize standard quantum field theory? Why does string theory force us to unify general relativity with the other forces of nature, while, as David Gross remarked at the end of his talk, standard quantum field theory makes it so difficult to incorporate general relativity? Why are there no ultraviolet divergences in string theory? And what happens to Einstein's conception of spacetime? I thought explaining these matters, even though what I'll be telling you about them is not extremely contemporary, is possibly suitable for a session devoted to the centenary of general relativity. Anyone who studied physics is familiar with the fact that while physics, like history, does not precisely repeat itself, it rhymes with similar structures at different scales of lengths and energies. For example, the gravitational waves we heard about in the second talk are analogous to light waves or water waves, and many other kinds of waves that are studied in many different systems at many different length scales. We'll begin today with one of those rhymes, an analogy between the problem of quantum gravity and the theory of a single particle. Now, in Einstein's theory of gravity, the geometry of space-time is dynamical, rather than space-time being something that exists beforehand in which physics unfolds. How space-time unfolds is part of the theory. And what that means is that, although we don't really understand it, quantum gravity somehow should be some sort of theory in which, at least from a macroscopic point of view, we average, in a quantum mechanical sense, over all possible geometries of space-time. In the classical theory, there's a definite space-time geometry that unfolds. Quantum mechanics involves fluctuations in which, in a quantum mechanical sense, we would have to average over all possible geometries. We don't know to what extent this description is valid microscopically, but at least macroscopically, that's what it ought to mean to quantize the geometry of space-time. Now, in the simplest case, the averaging is done with the weight factor, which is the exponential of minus the Einstein-Hilbert action. So I've written the Einstein-Hilbert action in the traditional way. R is the curvature scalar, and lambda is the cosmological constant, which, as David Gross remarked, was introduced by Einstein in his first attempt at a cosmological model. Nowadays, we know it's important in the real world. Now, we could add matter fields, but general relativity in 4 dimensions is a perfectly interesting theory without matter fields. So we could think of this as the purest version of Einstein's theory, where you consider only gravity and not matter fields. So the physical dimension of space-time, at least macroscopically, is 4. So we're interested in Einstein's theory in 4 space-time dimensions. And that's hard, and we don't understand it quantum mechanically. What would happen to us if we practiced by making a theory like this in which the space-time dimension was 1 instead of 4? Well, one thing that would happen is that there are not many options for a one-manifold. I've more or less drawn the only possible one-dimensional manifolds. And in contrast to the four-dimensional case, there's no Riemann curvature tensor in one dimension, so there's no close analog of the Einstein-Hilbert action. But Einstein's fundamental idea was really not the Einstein-Hilbert action, but the principle of equivalence, which he developed into the idea that the geometry of space-time is fluctuating, that the fundamental laws are laws in which the geometry has to be determined by solving equations. And we can do that in one dimension even though there isn't an Einstein-Hilbert action. But to do it in an interesting way, now we have to include matter fields. So we can still make a non-trivial theory of quantum gravity, by which I mean a theory where the geometry fluctuates, but we'll have to include matter to make an interesting theory. So in the simplest case, we take the matter to consist of some scalar fields, which I've called x sub I, where I runs from 1 to d. D matter fields. And we'll write down the most obvious action. We follow Einstein's general rules that we're supposed to write a generally covariant action. So we have a 1-by-1 metric tensor that we use to write the action. I've included a cosmological constant, but I've renamed it as m squared over 2. And then the scalar fields, for the scalar fields, I've written the most obvious generally covariant action functional, which is just the square of the time derivative of a scalar field, but weighted the way Einstein would tell us to weight it. Now, if we introduce the canonical momentum just as in classical mechanics, the momentum is x dot, the time derivative of x, then the Einstein field equation, which is supposed to be the field equation that we get by varying the action with respect to the metric tensor, the Einstein field equation in this example is going to be a very simple equation. It just says that p squared plus m squared is 0. But quantum mechanically, p is a derivative with respect to x, and we would interpret p squared plus m squared as minus d squared by dx squared plus m squared. And the statement that it's 0 quantum mechanically really means that this operator should annihilate the quantum mechanical wave function. So the content of our general relativity theory in one dimension tells us that this operator should annihilate the quantum wave function. Well, that's an operator that you may have seen before if you've studied classical general relativity. The equation we found is the relativistic Klein-Gordon equation in d dimensions, but in Euclidean signature. If we want to give a sensible physical interpretation, we probably should reverse the sign of the action for one of the scalar fields, so the action will look more like this, where one of the scalars, which I'm calling x0, has an unusual sign of the action. And now the equation obeyed by the wave function is a Klein-Gordon equation in Lorentz signature. So we found an exactly soluble model of quantum gravity in one dimension, and what it describes is a spin-zero particle of mass m propagating in d-dimensional Minkowski spacetime. So what we found is certainly something that textbooks on classical general relativity describe, but they don't necessarily describe it in the way I've explained as coming from one-dimensional quantum gravity. Actually, we could replace Minkowski spacetime by any d-dimensional spacetime m with the Lorentz signature metric Gij, and then the action looks like so. And the equation obeyed by the wave function will now be a Klein-Gordon equation on our spacetime m. So we could get not just the Klein-Gordon equation in flat spacetime, but the general relativistic version of the Klein-Gordon equation. Where here general relativistic means in 4 dimensions or in d dimensions, the real general relativistic equation we get from our baby version of quantum gravity in 1 dimension. So we got the massive Klein-Gordon equation in a curved spacetime. Now, to continue though, I want to make the equations a little simpler and more familiar, so I'll abbreviate Gij, Pi, Pj as p squared, and I'll also write formulas in Euclidean signature just to avoid having to explain a few details. Now let's calculate the amplitude for a particle to start at a point x in spacetime and end at another point y. So here's a picture. The particle started at x and ended at y, and it followed some path. In classical physics, we would solve Newton's laws to determine what should have been the path. But in quantum mechanics, any path is allowed, but a path has to be weighted with the exponential of minus the action. So, but what is the action? Well, but in quantum gravity, there's not only a path in spacetime, but there's also a one-dimensional geometry. So part of the process of evaluating the amplitude to go from x to y in quantum gravity is to integrate over the metric on the one manifold modulo diffeomorphisms. In other words, modulo what Einstein called general coordinate transformations. But up to diffeomorphism or general coordinate transformation, a one manifold has only one invariant, the total length tau. No matter what the metric is on this path, the only invariant of a one-dimensional geometry is the total length tau, which we'll interpret as the elapsed proper time. So we'll have to calculate the amplitude for the particle to get from x to y, where an arbitrary proper time tau might elapse along the path, and it might get from x to y along an arbitrary path. Well, first we'll do this keeping tau fixed. And if tau is going to be fixed, we can take any one metric that has length tau. For example, the one metric could be 1, where the one manifold is parameterized by a time variable t that goes from 0 to tau. So then, keeping tau fixed, we simply integrate over all paths the particle might follow in a way that was described 50 or 60 years ago by Richard Feynman when he introduced Feynman integrals. And then the precise calculation I'll describe is the first example in the book of Feynman and Hibbs on path integrals. So on a one manifold parameterized by time that goes from 0 to tau, we have to integrate over all paths that start at x at time 0 and end at y at time tau. And the action started as being a general relativistic action, but once we set gtt to 1, it's simply a standard non-relativistic action for a point particle. So it's literally the same action that you would read about in Feynman and Hibbs, where they explain how to do this basic path integral. So according to Feynman, the integral over all paths, so the Hamiltonian of the non-relativistic quantum mechanics is p squared plus m squared, and according to Feynman, the result of the path integral is the matrix element of the exponential of minus tau h, where h is the Hamiltonian. So h can be diagonalized by going to momentum space. So to get the amplitude to propagate from y to x, we integrate over all momenta. If the momentum is p, the amplitude is e to the ip dot y minus x, and then we include the matrix element in a plane wave state of the exponential of minus tau times the Hamiltonian. So this would be the amplitude to get from x to y in a proper time tau. But we have to remember to do the gravitational part of the path integral, which here just means to integrate over the elapsed proper time. So the complete path integral for our problem, integrating over all metrics and all paths, modulo diffeomorphisms, gives the integral from 0 to infinity over the proper time of what we had for fixed proper time, which was this. So we have to integrate this expression over tau, and that just turns the exponential of minus tau times p squared plus m squared into 1 over p squared plus m squared. So finally, our answer is what's written here. That's the amplitude to propagate from x to y, and it's the standard Feynman propagator in Euclidean signature. A similar derivation in Lorentz signature would give the correct Lorentz signature Feynman propagator with the I epsilon. So we've interpreted a free particle in d-dimensional spacetime in terms of one-dimensional quantum gravity. How can we include interactions? There's actually a perfectly natural way to do this. There are not a lot of smooth one-manifolds, but there's a large supply of singular one-manifolds in the form of graphs. There's a graph, for example. Our quantum gravity action makes sense on such a graph. We just take the same action we used before, summed over all the line segments that make up the graph. So we integrate the action over this segment, and this segment, and this segment, and so on. So now to do the quantum gravity path integral, well, the quantum gravity part of it is that we integrate over all metrics on the graph up to general coordinate transformations, in other words, up to diffeomorphisms. But the only invariants are the total lengths or proper times of each of the segments. So I've labeled some of the line segments by a proper time variable, tau 1, tau 2, or tau 3. I didn't label all of them. The natural amplitude to compute is one in which we hold fixed the positions of the external particles and integrate over all the proper time variables and all the paths the particles follow on the line segments. Now, for the moment, we keep fixed the proper times and just integrate over the paths. Here we observe that if we specify the positions at the vertices, and therefore on each end of each line segment, so this line segment goes from y1 to y2, this one goes from y1 to x1, but now all vertices and external endpoints are completely labeled, so each end of each line segment is labeled, and we specify at what point in space-time that should be. So once this is done, the computation we have to do on each line segment is the same as before and gives the Feynman propagator. So we have a graph, and to each segment in the graph we have a Feynman propagator, but we still have to integrate over the internal positions y1 up to y4 in this example. The integration over the y's will just impose momentum conservation at vertices, and we arrive at Feynman's recipe to compute the amplitude associated to a Feynman graph. We take a Feynman propagator for each line and an integration over all momenta subject to momentum conservation. So if you're familiar with Feynman graphs, you'll recognize that what we've arrived at is what Feynman said to do, and otherwise, just accept that somehow this quantum gravity procedure applied to a one-dimensional world with a space-time that was a graph has materialized Feynman's recipe for computing a scattering amplitude in standard quantum field theory. So we've arrived at one of nature's rhymes. If we imitate in one dimension what we would expect to do in 4 dimensions to describe quantum gravity, we arrive not at quantum gravity in space-time, but at something that's certainly important in physics. We have arrived at ordinary quantum field theory in a possibly curved space-time. We've not arrived at quantum gravity, but we've arrived at quantum field theory. In other words, at the mathematical framework that's used in the standard model of particle physics in a given space-time, which could have been flat or it could have been curved. In the example I gave, the ordinary quantum field theory we arrived at is scalar phi cube theory because of the particular matter system we started with, and assuming we take the graphs to have cubic vertices. Quartic vertices, for instance, would have given phi 4 theory, and a different matter system would give fields of different spins. So many, or maybe all, quantum field theories in d dimensions can be derived in this sense from quantum gravity in 1 dimension. So that's one of nature's rhymes. But there's actually a much more perfect rhyme if we repeat this in 2 dimensions, that is, for a string instead of a particle. So one thing we run into immediately is that a 2-manifold sigma can be curved. I've drawn one, and it's curved. So you see, in general, gravity in 2 dimensions will not be nearly as simple as it is in 1 dimension. There will be a Ricci scalar and an Einstein-Hilbert action. So the integral over 2-dimensional metrics promises to not be trivial. This is related to the following fact. A 2-dimensional metric in general is a 2x2 symmetric matrix. So it's a 2x2 matrix where G21 equals G12, but it has 3 independent matrix elements. This one, and this one. Now, of the three matrix elements in the matrix, you can remove two of them by diffeomorphism that locally depends on two arbitrary functions. But you only can remove two of the three functions, so you really will be left with one arbitrary function in the metric tensor to integrate over. And if that's the answer, you will not get a close analog of what I explained for the particle. But now we notice that the obvious analog of the action function that we used for the particle, which is this one, where now I simply integrate in 2 dimensions instead of 1, but I write the obvious analog of the action we used for the particle, is conformally invariant. That is, it's invariant under multiplying the metric tensor by any positive function, e to the phi. If we require conformal invariance as well as diffeomorphism invariance, then this is enough to make any metric on sigma locally trivial, locally equivalent to the Euclidean metric, which is analogous to what we had when we were studying the point particle. And some very pretty 19th century mathematics now comes into play. Here I've drawn an example of a Feynman diagram. I've picked a simple one with only 3 propagators, and therefore the one-dimensional geometry only depends on 3 proper time parameters. Now below I've drawn the string theory analog of this Feynman graph, which I've achieved by slightly thickening every line into a tube that represents the propagation not of a point particle but of a closed string. And then at every vertex I've smoothed out so that the tubes join smoothly. And now it turns out that, as in the one-dimensional case, the metric can be parameterized by finitely many parameters. It can be parameterized up to general coordinate transformations and also rescalings of the metric, which are called Weyl transformations. So there's a fairly close analog with the classical case, but there are a few important differences. One difference is that the parameters are complex rather than real. But a second difference, which will be more important today, is that the range of these parameters is restricted in a way that allows no possibility for an ultraviolet divergence. So we'll make a theory that in some ways is analogous to the traditional one, but it is a theory in which there can't be an ultraviolet divergence. So I've drawn another picture to underscore how a two-manifold is understood as a generalization of a Feynman graph. So I drew one example here, but here's another example. In this case, this is a one-loop Feynman graph for 2-particle scattering. 2 particles came in and 2 go out. And on the right, I've thickened it slightly, replacing the particles by tubes. So the line here is the world line of a particle. The tube is the world tube of a string. And now the tubes join smoothly. So the singular 1-manifold with vertices is replaced by a smooth 2-manifold. But here is a one-loop Feynman diagram for 2 going to 2 scattering in the one-dimensional or 2-dimensional case. Now I come to a deeper rhyme than the one we've told about before. With one-dimensional quantum gravity, we arrived at quantum field theory in a space-time that might be curved. But we did not arrive at quantum gravity in space-time. The reason we did not get quantum gravity in space-time, to state it in a very succinct but slightly perhaps abstract way, is that in quantum mechanics, there is no correspondence between operators and states. If you read a book on quantum mechanics, or if you take a course on quantum mechanics, you'll learn about the quantum wave function, which is a state in the Hilbert space. You'll also learn about operators like the position or the momentum that act on the quantum states. But nobody ever tells you that there's a map between operators and states, because in general, in quantum mechanics, there isn't. So what we did with our one-dimensional quantum gravity was we considered the one-dimensional theory with a dynamical metric tensor, and then we arrived at Feynman diagrams. And the external states in the Feynman diagrams were just the states in this quantum mechanics. Remember, the first thing we did was to quantize the quantum mechanics and get the Klein-Gordon equation. And the quantum mechanical states were the solutions of the Klein-Gordon equation. A deformation of the space-time metric would appear where? Well, the space-time metric appears in the action. So if we change the metric a little bit, that would represent a change in the action. And the action would change by the integral over time of the change in the Lagrangian density. So if I change the space-time metric Gij a little bit, the Lagrangian density will change by this operator curly O. So that operator would represent a change in the space-time metric, but not a state in the quantum mechanics. So as I said, operators in quantum mechanics do not correspond to states. If you ever studied quantum mechanics, you weren't told that no one ever told you of a correspondence between operators and states. And that's why the one-dimensional theory did not describe quantum gravity in space-time. In fact, the one-dimensional theory as I presented it led to phi-cube theory in space-time rather than quantum gravity. An operator O, such as the one describing a change in the space-time metric, appears on an internal line in the Feynman diagram, not an external line. So you see, to calculate the effects of a perturbation, we insert the integral of the perturbation, where we integrate over the position on the graph where the operator is inserted. I just drew one possible insertion point. It could be inserted anywhere, but it's not particularly at the external points that represent the particles in the quantum mechanics, or the states in the quantum mechanics. So because there is no correspondence between operators and states in quantum mechanics, the objects which are scattered in our Feynman diagrams do not generically describe fluctuations in the geometry of spacetime. So we arrived at quantum field theory in a fixed spacetime, but not at quantum gravity in spacetime. But in conformal field theory, and remember, to make the theory work in 2 dimensions, we had to assume conformal invariance. In conformal field theory, there is a correspondence between operators and states, which actually is important not just for string theorists, but also in statistical mechanics and certain areas of condensed matter physics. So the operator in the 2-dimensional case, the operator that represents a fluctuation in the space-time metric, automatically does represent a state in the quantum mechanics. And therefore, the theory does describe quantum gravity in spacetime. So, since the correspondence between operators and states that exists in 2 dimensions but not in 1 is the reason that string theory describes quantum gravity in spacetime, I want to take a few moments to explain it. It comes from a 19th century relation between 2 pictures that are conformally equivalent. So here I've drawn a 2-manifold, a 2-dimensional worldsheet, as we call it in the jargon, and in that red dot is a point at which an operator might be inserted. But 19th century mathematicians discovered that if you remove the point from that red point from the 2-manifold, the metric on the 2-manifold is conformally equivalent to this one with a long tube going off. Now, if a long tube goes off, we'd say that what is at the end of the long tube would be a state in the quantum mechanics. Well, in this picture, we'd say that at a point on the 2-manifold is inserted an operator in the quantum mechanics that represents a fluctuation in the action, perhaps coming from a change in the metric of spacetime. So the conformal equivalence between these 2 pictures is the reason that while in 1 dimension we got quantum field theory in spacetime, in 2 dimensions we get quantum gravity in spacetime. I therefore will take a moment to explain in more detail this conformal mapping. For the basic idea, we write the metric of a plane, which I've written, a 2-dimensional plane, a flat plane. I've written the metric of a plane in polar coordinates. We think of inserting an operator at the origin of polar coordinates. Now, the origin of polar coordinates is the point we're going to remove. And after we remove it, we make a conformal transformation, multiplying the metric by 1 over r squared. Here's the new metric. And now I introduce a new variable, u, which is log r. It goes from minus infinity to infinity. And now the new metric is just a flat metric again, but now on a cylinder because phi is an angular variable. So I have described a conformal mapping from the plane minus the origin to the cylinder. So this conformal mapping gives an equivalence between an operator inserted at this point and an initial state in the quantum mechanics that comes in from minus infinity on the tube. That conformal mapping is the reason that, unlike in the one-dimensional case, string theory leads to a description of quantum gravity in space-time. So we arrived at quantum gravity in space-time, but we could have tried to arrive at quantum gravity in space-time by taking the Einstein-Hilbert action, reading Dirac's book about the passage from classical mechanics to quantum mechanics, and formally following the recipe. In fact, people did that starting in the 30s. But it doesn't work well because one runs into intractable ultraviolet divergences, which in the 30s seems only a little bit worse than the analogous divergences in electromagnetism. But by the 1950s, when people had learned to tame the divergences in quantum electrodynamics, and even more later when the full standard model of particle physics was developed, it became clear that the methods that tame the ultraviolet divergences in quantum field theory without gravity do not work for gravity. So now we should ask if this alternative approach to quantum gravity in space-time eliminates the ultraviolet divergences, which plague a naive attempt to quantize Einstein's gravity according to textbook rules. So I want to spend a few minutes to explain why this type of theory does not have ultraviolet divergences. Well, first of all, where do ultraviolet divergences come from in field theory? They come from the case that all the proper time variables in a loop go to 0. So I've drawn a one-loop diagram that we discussed before, and now I've labeled all of the internal lines by proper time variables, t1, tau1, tau2, and so on up to tau4. And to evaluate the Feynman amplitude, or if you wish, to evaluate the one-dimensional quantum gravity path integral as we interpreted it, we have to integrate over these proper time variables. In the example shown, ultraviolet divergences can come when all the proper time variables going around the loop simultaneously go to 0, so that the total proper time elapsed around the loop vanishes. Now, it's true, as I said, that a Riemann surface is just a fancy 19th century name for the two-dimensional manifolds that we are using instead of Feynman graphs. It's true that a Riemann surface can be described by parameters that roughly mirror the proper time variables of a Feynman graph. So here's a picture I drew before with the proper time parameters and their analogs in 2 dimensions. But as I said before, there are a couple of crucial differences. And one very important difference, which is the reason that there are no ultraviolet divergences in string theory, is that although the proper time variables tau of a Feynman graph cover the whole range from 0 to infinity, the corresponding 2-dimensional parameters, tau hat, are bounded away from 0. So the region of integration that leads to the infinities of a Feynman graph are simply absent when we replace conventional Feynman graphs that arise from one-dimensional quantum gravity with their string theory analogs that arise from 2-dimensional quantum gravity. So what I've just said is a matter of some more 19th century mathematics, and I won't give a complete explanation, but I will give an illustrative example. But first let's just say again, given a Feynman diagram, we can make a corresponding Riemann surface, but the mapping only works well if the proper time variables tau I are not too small. So the region that leads to trouble in conventional quantum field theory is lost when we go to string theory, while the physical phenomena that are important in quantum field theory and that we observe really have to do with large tau, and those persist in string theory. So I won't give a general explanation, but I'll explain how it works for the one-loop cosmological constant. So the Feynman diagram is simply a circle with a single proper time parameter, tau, which is the circumference of the circle. And the resulting expression for the one-loop cosmological constant is what I've drawn here, written here, where we integrate overall tau from 0 to infinity. H is the particle Hamiltonian. And the trace is a trace over all states of the particle Hilbert space. And the integral diverges at small tau because of the momentum integration that's part of the trace. So technically, when you perform this trace, you get a badly behaved function of tau, or more exactly, it behaves badly for small tau, tau going to 0. And that's the famous ultraviolet divergence of quantum field theory. Now, going to string theory means replacing the classical one-loop diagram by its stringy counterpart, which is a two-dimensional manifold that's a torus. 19th century mathematicians showed that every torus is conformally invariant equivalent to a parallelogram in the plane with opposite sides identified. You glue the top to the bottom and the left to the right. But to explain the main idea without extraneous details and keep our chairman happy regarding the time, I'll consider only rectangles instead of parallelograms. So we'll label the height and base of the rectangle as s and t. So we have a rectangle in the plane whose height is s and whose base is t. But you see, only the ratio t over s, which I'll call u, is conformally invariant. So in a conformally invariant theory, we will integrate not over t and s separately, but only over u. And also, since it's arbitrary what we mean by the height and what's the base of the rectangle, we're free to exchange s and t. By exchanging s and t, we can consider only the case, well, exchanging s and t exchanges u with 1 over u. So up to a general coordinate transformation of our two-dimensional world, u is the same as 1 over u, which means we can restrict to, well, these statements mean we can restrict to the region where t is no bigger than s, no smaller than s, and equivalently we take the range of u to be from 1 to infinity. Now, the proper time parameter tau of the particle corresponds to u in string theory. And the key difference is that instead of tau, which goes from 0 to infinity, we have u, which goes from 1 to infinity. So, although the one-loop cosmological constant in field theory is given by this textbook formula, in the approximation of considering only rectangles and not parallelograms, the string theory analog is almost the same, but the integral goes from 1 to infinity instead of from 0 to infinity. So we simply are missing the region that would have led to the trouble in field theory. There's no ultraviolet divergence because the lower limit on the integral is 1 instead of 0. And just for fun, I'll say if you include parallelograms, the lower limit becomes 1/2 root 3 instead of 1. But the important thing is that there still is a positive lower limit. So I've explained a special case, but this is a general story. The stringy formulas generalize the field theory formulas, but without the region that can give ultraviolet divergences in field theory. The infrared region lines up properly between field theory and string theory, and that's why a string theory can imitate field theory in its predictions for the behavior at low energies or at long times and distances, and that's why string theory can be compatible with physics as we developed it in the 20th century. But the region that gives the ultraviolet divergences disappears. And so there's no difficulty in going to quantum gravity, but you can't avoid going to quantum gravity because of the operator state correspondence that I told you about. Now I want to use the last few minutes to explain at least partly in what sense space-time emerges from something deeper if string theory is correct. And you'll hear a fuller and probably more contemporary explanation in the next lecture by Juan Maldacena. We'll focus on the following fact. The spacetime M with its metric tensor Gij of x was encoded as the data that enabled us to define a two-dimensional conformal field theory that we used in this construction. Moreover, that's the only way that spacetime entered the story. we could have used in this construction a different two-dimensional conformal field theory. Now, if the metric is slowly varying compared to the natural length scale on which string theory modifies conventional physics, so that the radius of curvature is everywhere large, then the Lagrangian that we use to describe the two-dimensional conformal field theory is weakly coupled and illuminating. This is the situation in which string theory matches to ordinary physics that we are familiar with. We may say that in this situation, the theory has a semiclassical interpretation in terms of strings in space-time, and this description will reduce at low energies to an interpretation in terms of particles and fields in space-time. When we get away from a semiclassical limit, the Lagrangian is not so useful, and the theory does not have any particular interpretation in terms of strings in space-time. In fact, the following type of situation very frequently occurs. What I've drawn here schematically, this region is meant to schematically indicate a family of two-dimensional conformal field theories that depends on two parameters that parameterize this region. And generically, there's no particular interpretation in space-time, but there's a limit where you discover strings in a space-time M1, but there's another limit where you find strings in a different space-time M2, and in a third limit you discover M3. So generically, there's no particular space-time at all, but in different limits, one space-time or another might emerge. And lots of other non-classical things can happen. For example, in a situation where in classical general relativity, the space-time develops a singularity, the two-dimensional conformal field theory may remain perfectly good, meaning that the physical situation in string theory is perfectly sensible. So we can say that from this point of view, space-time emerges from a seemingly more fundamental concept of two-dimensional conformal field theory. From this point of view, a more fundamental concept is the two-dimensional conformal field theory that might be described in terms of a space-time, but not necessarily. Space-time emerges in a limit from a more fundamental concept. In general, a string theory comes with no particular space-time interpretation, but such an interpretation can emerge in a suitable limit, somewhat as classical mechanics sometimes arises as a limit of quantum mechanics, though you can study a quantum system that's very far from any classical limit. Now, this is not a complete explanation of the sense in which, in the context of string theory, space-time emerges from something deeper. A completely different side of the story, which you'll perhaps hear about in the next lecture, involves quantum mechanics and the duality between gauge theory and gravity. But what I've described is certainly one important piece of the puzzle. It's perhaps the piece that's best understood even today, although that's arguable, but certainly it's the best understood piece that's been best understood for longest. It's at least a partial insight about how space-time as conceived by Einstein can emerge from something deeper. And thus, I hope this topic has been suitable in a session devoted to the centennial of general relativity. Thank you.